Something just happened at Lake Oroville that should not be physically possible. A 23-foot surge in water level. Overnight, with no rain, no upstream release, no landslides, no malfunctioning gauges, nothing that should cause even a ripple, let alone a vertical wall of water. It wasn't a clerical error. It wasn't a tech glitch. Every single system confirmed it. Satellite imagery, radar, telemetry, gauge readings, upstream flow sensors, even CCTV footage. All sensed, all showed the same thing.
If you enjoyed this breakdown, don't forget to like, subscribe, and drop a comment. Your feedback helps shape what we cover next, and you being here keeps the conversation going. Thanks for watching. See you in the next one.
A vertical spike in water volume that science says shouldn't exist under these conditions. And yet it happened. The implications aren't just local. This is Lake Oroville we're talking about. The crown jewel of California's water infrastructure. A 3.5 million acre-foot reservoir responsible for quenching the thirst of 27 million people, irrigating a huge chunk of the state's farmland, and powering nearly a gigawatt of hydroelectric energy. When Oroville behaves erratically, the rest of California flinches. And right now, it's not just misbehaving. It's breaking the rules of hydrology. Start with what didn't cause this. There was no rainfall. Not even a drizzle. Zero atmospheric input. No snowmelt anomalies. No upstream dam releases. No landslides or topographic shifts that could push water into the basin. And certainly no operational tinkering. Every human-controlled input was locked down. Engineers triple-checked, then quadruple-checked. This wasn't some obscure single sensor reading either. Redundant systems across multiple agencies all reported the same surge. Staff gauges on site, satellite composites from above, pressure transducers in the lakebed, even manual frame-by-frame analysis of nighttime CCTV footage. Every angle, every method, confirmed the same story. Between 2 o'clock and 3 a.m., Lake Oroville's water level rose by 23 feet. The surge was real. The cause, however, is another story. Because if it didn't come from the sky, and it didn't come from upstream, and it didn't come from human error, then it had to come from below. That's when things got even weirder. At exactly 2:17 a.m. right as the surge began, a microseismic tremor was recorded along the eastern shore of the lake. Magnitude 2.1. Not enough to shake houses, but enough to move something. And it didn't just happen near the surge. It happened with it. A perfect timestamp match. Seismologists cross-referenced the event with water telemetry. The alignment was undeniable. Whatever happened under the lakebed was not random tectonic background noise. It was part of the same event. Next came the chemical signatures. Water samples from the reservoir showed anomalies, elevated electrical conductivity, unusual mineral content, and most telling of all, shifts in isotopic composition, specifically oxygen-18 and deuterium levels. These aren't casual markers. They're geological timestamps. They tell you where the water came from and how long it's been down there. And what they revealed was chilling. The surge water didn't come from rain. It didn't come from snowpack. It came from deep, pressurized aquifers, mineral-rich groundwater that's been trapped underground for potentially centuries. Water with a geochemical fingerprint that screams crustal origin, mobilized by force, propelled upward. In other words, the lake filled itself from below. This brings us to the tectonics. The area beneath Lake Oroville isn't just any chunk of earth, it's a geological crossroads, a spaghetti mess of ancient fault lines and buried aquifers. And when those two systems intersect under pressure, you get what geophysicists call fault valve behavior. In plain terms, the earth opened a valve. Under certain tectonic or hydraulic conditions, subsurface fractures can act like one-way spigots. They release massive amounts of pressurized water upward through transient conduits directly into reservoirs like Oroville. Not gradually, not predictably, but explosively. That seems to be exactly what happened. The tremor triggered a release. A deep, unseen vault of groundwater shot up into the reservoir. And because our monitoring systems are almost entirely surface-focused, nobody saw it coming. Here's the kicker. Our current safety protocols weren't designed for this. Dam infrastructure, especially in the US, is built on a foundation of predictability, weather patterns, surface inflow, linear causality, the kind of stuff you can measure with a rain gauge or track on a satellite. Subsurface dynamics, basically ignored. But the Oroville surge blew that model out of the water literally. We're not talking about a clogged culvert or a missed inspection. We're talking about an entire class of hazards that operate underground, beyond our usual line of sight. And the only reason we noticed this time is because the water shot up high enough to breach the surface.
If you enjoyed this breakdown, don't forget to like, subscribe, and drop a comment. Your feedback helps shape what we cover next, and you being here keeps the conversation going. Thanks for watching. See you in the next one.
Now take a second to remember 2017, the Oroville Dam crisis, when the emergency spillway started disintegrating, and nearly 200,000 people had to evacuate in the largest dam-related emergency in U.S. history. That was a surface failure and engineering oversight. It was terrifying, but at least we understood what was breaking. This is worse, because now, even the experts are saying they don't fully understand what's happening. And when engineers don't understand a system they're supposed to control, that's when things get dangerous. In fact, uncertainty is now one of the biggest risk factors facing infrastructure. Not corrosion, not cost, just not knowing. When you can't explain a 23-foot overnight surge in your state's most critical reservoir, you're flying blind. You default to worst-case assumptions. Emergency protocols kick in. Public trust starts to erode. And all it took was one anomaly. But this isn't just about Oroville. It's about a national system of aging dams operating well beyond their original design expectations. Infrastructure that was never built to interact with deep earth hydrology. Engineers assumed the ground was static, that if water wasn't coming from the sky or the river, it wasn't coming at all. That assumption just broke. The Oroville surge forces a hard truth into the spotlight. Our engineered systems are colliding with Earth's evolving dynamics. Faults shift, aquifers pressurize, climate stress builds, and somewhere in that mix, new classes of hazard emerge. Hazards that don't announce themselves with a rainstorm. They just appear, like a 23-foot wall of water rising from nothing. So what happens now? Scientists are scrambling. There's talk of installing deep well piezometers, denser seismic arrays, real-time isotope analyzers, anything to get eyes and ears deeper into the crust. Because until we understand what's happening down there, we're just waiting for the next surprise. And here's the part that really stings. This kind of subsurface surge might not be that rare. It might just be invisible. We've only been looking at the surface. And now that one reservoir just yelled loud enough to be heard, we're realizing how blind we've been. It's not a glitch. It's a warning. So what's the moral of the story? Simple. Don't underestimate the Earth, especially not when it's sitting beneath your most important infrastructure. And if the systems we rely on every day aren't being updated to account for what's moving deep below us, then they're not just outdated. They're dangerous. Let us know what you think. Does this mean we need a whole new way of monitoring infrastructure? Or was this just a freak geological event? Drop your thoughts in the comments. And if you want to stay ahead of stories like this, make sure to like, subscribe, and share this with someone who still thinks the ground beneath their feet is solid. Spoiler, it isn't. Here's the part no one wants to say out loud. If Lake Oroville can do this once, it can do it again. This wasn't a one-off atmospheric anomaly. It wasn't a surface flood event with known variables. It was a silent, invisible surge from within the Earth itself. And the only reason we know about it is because the numbers spiked high enough, fast enough, and across enough sensors that ignoring it became impossible. But what about the times it doesn't surge 23 feet overnight? What if there have been smaller, undetected discharges in the past, little pulses of crustal water nudging the reservoir upward by inches instead of feet? If we've never monitored the subsurface for these kinds of shifts, how would we know? The truth is, we wouldn't. And that's the real nightmare. This surge might be part of a long-running pattern. One we're only just beginning to detect. You can practically hear the gears grinding in the heads of hydrologists and engineers right now. If deep aquifer discharge into major reservoirs is possible, and not only possible, but measurable, then it changes the entire framework of water management. It upends flood risk models. It complicates long-term infrastructure planning. And it forces state and federal agencies to ask an uncomfortable question. What else don't we know? Because think about it, if your entire dam management strategy assumes that inflow comes from rain, snow, or upstream flow. But now you've got an unknown, unscheduled, unstoppable source of groundwater suddenly surging up through the lakebed. That's not just a blind spot. That's a structural vulnerability. Now, to their credit, scientists aren't throwing out random theories. They're not blaming aliens or glitches in the matrix. They're following the data. And that data is starting to build a coherent if unsettling storyline. We've got microseismic activity tied to precise water level shifts. We've got oxygen 18 and deuterium readings pointing directly to crustal reservoirs. We've got elevated conductivity and mineral traces in the water consistent with long isolated aquifer systems. And we've got geological surveys showing that the lakebed sits atop a dense web of fault lines, right where tectonic strain and aquifer pressure intersect. It's a geophysical cocktail. And Lake Oroville just took a massive, unexpected swig. What's striking is how these multiple lines of evidence, each potentially explainable on its own, gain serious weight when they align. If you just had a tremor, maybe it's nothing. If you just had strange isotopes, could be runoff contamination. But all at once, with a time-stamped 23-foot water spike, that's not noise. That's a pattern, a signature. And if this signature is showing up at Oroville, where else might it be hiding? That's the domino effect no one wants to talk about. California has dozens of reservoirs, hundreds of dams, many built mid-20th century, under a radically different understanding of geological risk. The entire system was designed assuming control, measurable, modelable, human-scale control. But what if the ground beneath that system is operating on a completely different logic? What if it doesn't care about spreadsheets or safety protocols? Worse yet, what if it's changing? Because let's not forget, the Sierra Nevada foothills where Lake Oroville lives are not exactly tectonically stable. They're alive. They shift. They crack. They store pressure. And if that pressure gets released in new, unfamiliar ways, then infrastructure sitting on top of it suddenly looks a lot less engineered and a lot more improvised. That's where the 2017 trauma re-enters the chat. People still remember watching the spillway erode in real time. The emergency evacuations. The frantic press conferences. The lingering sense that maybe, just maybe, we've been overestimating how much control we really have. That was a crisis rooted in surface failure. A literal crack in the concrete. This is different. This is the earth itself rising up. Not to break the dam, but to fill it. Which, paradoxically, might be even scarier. Because we don't know how to stop it. Or predict it. Or regulate it. You can't pour concrete over a fault line and expect it to behave. And here's where the systemic risk starts to spiral. When institutions can't explain a major anomaly, they panic. They default to worst-case thinking. They overcorrect or underprepare. And in the absence of clear cause, rumors take over. Distrust snowballs. That's what makes this moment so precarious. The Oroville surge isn't just a physical anomaly. It's a psychological one. It exposes how little margin of error we actually have, how quickly confidence can evaporate, and how deeply we've underinvested in understanding the systems beneath our systems. If you're wondering why we don't already have deep well sensors and real-time isotope analyzers in every major reservoir, you're not alone. Turns out, most dam monitoring tech is focused at or above the surface. Rain gauges, river flow sensors, satellite evapotranspiration data. It's all designed for classic hydrology. But deep earth hydrology, that's a whole different discipline. One that barely interfaces with civil engineering. And that disciplinary silo is now a major liability. The surge proves we need integrated models, multidisciplinary teams, instruments that listen to the crust, not just the clouds. Because here's what's really at stake. The longer we rely on outdated assumptions, the more we drift into a false sense of security. And when the next surge hits, and there will be a next surge, we may not be lucky enough to get a 23-foot warning that just raises eyebrows. It could overtop. It could stress infrastructure past the point of failure. It could come at the same time as a seismic event, a heat wave, or a grid failure. That's the nature of cascading, nonlinear risk. It doesn't send calendar invites. It stacks events like a Jenga tower, then pulls 3 blocks at once. And the systems we trust, our dams, our reservoirs, our emergency protocols, weren't built for that kind of instability. They were built for predictability, which no longer exists. So where does that leave us? In a word, exposed, but also finally alert. Because Oroville just gave us a gift, weirdly enough. A chance to see what's coming. A warning shot we can actually study. It's a flashing red light telling engineers, hey, the game's changed. It's telling legislators, you need to fund better monitoring now. And it's telling the public, this isn't the drill. The lake surged 23 feet, without rain, without warning, without precedent. And that means the old rules don't apply anymore. So, what's next? You tell us. Let's get one thing clear, this is not just about water levels anymore. This is about the illusion of control. Because when your most carefully monitored, obsessively engineered reservoir can suddenly rise 23 feet overnight without a drop of rain, what else is hiding in plain sight? What makes the Oroville surge so jarring isn't just the volume of water. It's the violation of assumptions. Every dam engineer, Every hydrologist, every risk modeler has always worked off a core belief that changes in water level have a cause, a reason, a chain of events that starts somewhere: logical weather, runoff, inflow, and ends in the reservoir. That belief just broke. And let's not pretend this is just an academic problem. Oroville is the linchpin of California's entire water system. It holds back a lake the size of a small country. It keeps farms alive, cities hydrated, lights on. When it moves, the ripple effects aren't metaphorical. They're very, very real. So what happens when the public hears, "We don't know why the water rose"? What happens when the governor asks for answers, and the best the experts can offer is, it came from deep underground, maybe through a fault valve system triggered by seismic strain and crustal fluid migration, but we can't be sure. You know what that sounds like to most people: panic. It sounds like no one's steering the ship. And it's not because the scientists aren't doing their jobs. They are. They're racing against the clock, digging into isotopic profiles, comparing geomechanical models, pulling decades of seismic logs. But the scary part, this is uncharted territory. There's no playbook for massive subsurface groundwater surge into a critical reservoir. We built our dams on the idea that the land underneath them is passive, that it behaves, but the land doesn't behave. It shifts, it pulses, it changes on timescales we barely understand. And sometimes, like now, it sends up a 23-foot message that says, "You forgot about me." Let's zoom out for a second. Subsurface dynamics have always been treated like background noise, a curiosity for geologists, not a frontline risk factor. But the Oroville surge just shoved those dynamics right to the top of the risk register. Fault lines, aquifer pressures, isotopic anomalies, these aren't abstract concepts anymore. They're the new weather, and they're unpredictable. And here's where it gets especially uncomfortable. You can't retrofit a dam for deep earth behavior with a quick patch. There's no one-size-fits-all solution for tectonic aquifer release. It requires new tools, new science, new budgets. It requires admitting that maybe, just maybe, we've been flying blind on some of the most important infrastructure in the country. So the question becomes, will we listen? Will the Oroville event be the thing that finally forces agencies to fund deep monitoring? Will engineers start treating the earth under the dam as part of the system, not just the ground it sits on? Because if not, we're playing geological roulette. The earth gave us a warning. It lifted a reservoir by 23 feet in the dead of night, with no storm clouds in sight. That's not just a fluke. That's a message. So now it's up to us. What are we going to do with it? Drop your thoughts in the comments. Hit that like button if you think geology should be taken seriously in infrastructure planning. And subscribe for more stories where the planet reminds us who's really in charge. Because sometimes, the biggest shock isn't what happens above ground, it's what we never saw coming from below. Thanks so much for watching. If you made it all the way to the end, you're officially part of the small percentage of people who don't just click away, and that means a lot. Before you go, I'd love to hear from you. Drop a comment below and tell me your thoughts, your ideas, or even what you'd like to see next. I read every single one of them, and your feedback genuinely shapes the direction of this channel. If you enjoyed the video, tap that like button. It tells YouTube this content is worth sharing. And if you haven't already, hit subscribe and turn on notifications so you don't miss the next upload. We've got more exciting videos coming, and trust me, you'll want to be here for them. This channel is just getting started, and your support helps it grow faster than you realize. Thank you again for spending a part of your day here with me. Stay curious, stay motivated, and as always, take care of yourself. Until next time, I'll see you in the next video.